Hello friends, so today we are going to solve questions from modern physics, and these questions are from the year 2019, and today we are going to solve 10 questions, and all these 10 questions are from the main. And for the year 2019, this is part 2 of 2019. In the part 1 we covered 15 questions of 2019 and all those questions from the mains only. So first question, it states that the magnetic field associated with the light wave is given at the origin by the equation. So equation is given: if this light falls on a silver plate having a work function of 4.7 electron volt, what will be the maximum kinetic energy of the photoelectrons? So we are given the equation for our magnetic field, and from this equation of magnetic field we have to find out the value of the frequency. So we can write this, you can say the given equation can also be written as B is equal to B naught sine of pi into 10 to the power 7 C multiplied by T and plus B naught sine of, this can be written as 2 pi into 10 to the power 7 times Ct. So in this particular equation we are going to have two value of frequency. One value of frequency will be pi and other value of frequency will be our 2 pi. Okay. Or we can also say that they are having two different, this electromagnetic wave is having two different frequencies. Okay. Therefore you can say there are two electromagnetic waves with different frequency, but we have to keep in mind that our kinetic energy should be maximum. So in order for the kinetic energy to maximum, we are going to take a higher frequency. You can say to get maximum kinetic energy, we take photon with higher frequency. With higher frequency. Therefore, we can write that value of omega will be equal to 2 pi into 10 to the power 7 and multiply by c, where c is the speed of the light. And so we can find out energy, and we can say that according to Einstein's mass energy relation, or we can say simply mass energy relation, we can say our E is equal to H multiplied by frequency, that is our nu, or in terms of omega it can be written as omega upon 2 pi. And we can just substitute the values. We get our energy E is equal to H is our 6.6 into 10 to the power minus 34. Omega is our 2 pi 10 to the power 7 multiplied by 3 into 10 to the power 8, and this we are having 2 pi. So 2 pi and 2 pi cancel out quite easily, and this and we can say that our energy and we can convert this into our electron volt. So let me (1.6 into 10 to the power minus 19), and this will be approximately equal to 12.4 electron volt. And we are supposed to find out kinetic energy. Okay, work function is given to us, so we can use now straightforward equation. We know that photoelectric equation this gives us our E is equal to 5 plus kinetic energy maximum, and we substitute the value that our kinetic energy maximum is equal to energy minus work function. Energy is our 12.4 minus work function is 4.7. This gives us 7.7 electron volt. So option number A is correct. Next question. It states that in a radioactive decay chain, the initial nucleus is 9032 thorium. At the end, there are 6 alpha particles and 4 beta particles which are emitted. If the end nucleus is ZXA, then A and Z are given by. So our initial nucleus that is our thorium, and this is 232 and 90, and it emits 6 alpha particle and 4 beta particles. So we can say that the emitted we are having 6 alpha and 4 beta particles, and we are going to find out value of A and Z, okay, for this X. So first of all, let us discuss our alpha decay. So we can write our alpha decay, and we know that our each alpha particle we have the value of A is our 4 and value of Z is equal to 2, and we are given that we are having 6 alpha particles. So you can say 6 alpha particles. So therefore we get our mass number, that is A will be equal to 24 and atomic number Z will be equal to 12. So after alpha decay we are going to get a intermediate nucleus. So you can say our intermediate nucleus after alpha decay, the value of A in the start was our 232 minus 24, this gives us 208, and value of Z is our 90 minus 12, giving us 78. Then we are having our beta decay. So beta decay, and in case of beta decay we know that our atomic number increases by 1. We can say each beta particle increases atomic number by 1, and we are having 4 beta particles. So we can say our 4 beta particles the value of Z will be coming to us as 78 plus 4, that is our 82. Therefore finally we are going to have value of A will be over 208 and value of Z will be equal to over 82. So this is 208 and 82. Option B is correct. Option B is correct. Next question. It states that Using a nuclear counter, the count rate of emitted particles from a radioactive source is measured. At t is equal to 0, it was 1600 counts per second, and t is equal to 8 seconds, it was 100 counts per second. The count rate observed as counts per second at t is equal to 6 seconds is close to. So we are given count rate at t0, so which basically we can say initial count, that is n0, and we are given count as time t is equal to 8 seconds, that is 100, we can call that as our n. Okay, and for 6 seconds we are going to find out. So we are given at t is equal to 0, our n0 is our 1600, and at t is equal to our 8 seconds, we are given that the value of n is our 100. And we are going to use exponential decay formula. Which gives us that our n of t is equal to our n0 e raised to power minus lambda t, and we put value of t as 8 seconds. Therefore we can write that our t 8 seconds, this can be written as our n of 8. So we get this as our n of 8 is equal to n0 e raised to power minus lambda 8. N of 8 is our 100, n0 is our 1600 e raised to power minus lambda 8. And from here we can find out value of our lambda. So we get this as e raised to power, this is 100. Therefore we can say that our e raised to power minus lambda 8 will be equal to 100 upon 1600, which will be 1 upon 16, and we can write that our this can be written as lambda is equal to natural log of 2 divided by 2. Okay. And we are supposed to find out at t is equal to 6. So we can say at t is equal to 6, we can write our n of 6 is equal to n0 e raised to power minus lambda 6. And we just found out value of our lambda, and n0 we know is our 1600, this becomes e raised to power, and we have this minus natural log of 2 and whole multiplied by 6. Okay. And we can just modify it, and we can write that our n of 6 is equal to 1600 e raised to power, this can be written as our, this 6 goes by 3, so we are left with this as minus 3 natural log of 2, which can be further written as 1600 and multiply by 2 raised to power minus 3, and this comes 1600 divided by 8, giving us 200. So option B is correct. Correct. Next question. It states that in given time t is equal to t naught, activity of two radio substances A and B are equal. After time t, the ratio of their activities Rb to Ra decreases according to e raised to power minus 3t. If half-life of A is natural log of 2, the half-life of B will be. So we are given at t is equal to 0, the activity of both are same, A and B. Therefore, we can say at t is equal to 0, our activity of A is equal to our activity of B. And it says that at t is equal to t, the ratio Rb upon Ra is equal to e raised to power minus 3t. And we are also given that our half-life of Ta is equal to natural log of 2. And we are supposed to find out the half-life period of B. And we can just use the activity decay formula. Activity decay formula, which gives us that our R of t is equal to R naught e raised to power minus lambda t. So we have two substances, so we can divide this formula into two parts. For first one, that is R of t is equal to R naught e raised to power minus lambda at, and we have our Rb t is equal to and R naught e raised to power minus lambda bt. And this R naught is same in both cases because it is equal to our initial. So we can just say they both are equal to our R naught. Now we can just take their ratio. So we can say that our Rb t upon Rat is equal to R naught e raised to power minus lambda bt, R naught e raised to power minus lambda at. R naught and R naught cancels out and exponents can be rearranged. We can write this as e raised to power minus, and we get this as lambda b minus lambda a multiplied by t. And this ratio is given as our e raised to power 3t. So we can, from here, we can equate that this ratio is equal to minus of 3t, which gives us that our lambda b minus lambda a is equal to 3. And half-life of A is given to us. So we can say that our lambda will be equal to, our standard formula is natural log of 2 divided by t half. So from here we can write a lambda A is equal to natural log of 2 and divided by half-life of A. We get this as half-life of A is given as natural log of 2. So this comes natural log of 2 divided by natural log of 2. It cancels out. It comes out to be 1. So lambda A is equal to 1. And therefore, can say that our lambda b is equal to 3 plus lambda a, which gives us 3 plus 1. Therefore, lambda b is equal to 4. And we need to find out the half-life of b. So we can say that our half-life of b that is our Tb will be equal to natural log of 2 divided by our lambda b, and this comes as natural log of 2 divided by 4. So half-life of A is natural log of 2 divided by 4. Option B is correct. Next question. It states that a sample of radioactive material A that has an activity of 10 has twice the number of nuclei as another sample of a different radioactive material B which has an activity of 20. The correct choices for half-lives of A and B would be. So we have two samples A and B, and their activity is given as 10 and 20, and number of nuclei of B is A is twice that of B. Okay. So we can say that our activity of A let us suppose this is our AA, it is given as 10, and we have activity of B that is our AB, it is given to us as 20, and number of nuclei of A for A is our suppose Na, and number of nuclei for B is suppose our Nb. So therefore the relation between Na and B, we can write our Na is equal to twice of our Nb. We have to find out their half-lives. Okay. So we can just use the activity formula. We can say activity formula gives us that our A is equal to lambda times N, and lambda we already know is our natural log of 2 divided by T half multiplied by N. So from here we can write that our A upon N will be equal to natural log of 2 divided by T half. So we have two substances, therefore we can write this formula as activity of A divided by number of nuclei of A will be equal to natural log of 2, and we have half-life of A. Similarly, we can write activity of B, number of B is equal to natural log of 2, half-life of B. We simply take their ratio. So we can say activity of our A divided by Na, activity of B divided by our Nb is equal to, this will be our natural log of 2 divided by Ta, natural log of 2 divided by Tb. Here natural log cancels out, so this comes as our Tb divided by Ta, and we already know the value of this activity of A is given to us as 10, so this becomes our 10, and Na divided by B is about 20, and 2 times, one second, this is 2 times NB, and this is divided by NB. Okay. And this TB by here, NB and NB cancels out, and this comes as 1 upon 4. So you can say that our TA is equal to 4 times TB. So therefore the correct option will be our, one second, TA is 4 times TB. Yeah, so option number D is correct. So this is our TA, which is 4 times 5, which is our TB, so giving us 20. So option D is correct. Next question. It states that consider an electron in a hydrogen atom revolving in its second excited state having radius 4.65 angstrom. The de-Broglie wavelength of this electron is. So here we are given that it is in second excited state. So obviously value of n is equal to 3. So we can use the Bohr quantization, and we can write Bohr quantization, which gives us 2 pi r is equal to n times lambda, and from here we can write our lambda is equal to 2 pi r divided by n. R and n are given to us, and we can say this is equal to about 2 pi, r is about 4.65, and n is our 3. So this lambda comes approximately equal to 9.73 angstrom. So option D is correct. D is correct. Next question. It states that a particle P is formed due to completely inelastic collision of particles x and y having de-Broglie wavelength as lambda x and lambda y respectively. If x and y were moving in opposite directions, then de-Broglie wavelength of P will be. So here we have to keep in mind that it is a completely inelastic, and x and y were moving in opposite direction. Okay. And so we can use the conservation of momentum, but for that we can use that the relationship de-Broglie wavelength which is our lambda. It is given as h upon p, which is momentum. So from here we can say our momentum p is equal to h upon lambda. So we have our two particles. So based on this we can say momentum of x is equal to h upon lambda x, and momentum of y is equal to h upon lambda y. So it is given that x and y are in opposite direction, moving in opposite direction. X and y are moving in opposite direction. Therefore, net momentum which will be momentum of a particle P will be equal to h upon lambda x minus h upon lambda y, and we can just take their modulus depending upon the magnitude, and we can take h as common, so this comes as h 1 upon lambda x minus 1 upon lambda y. And so for particle P, you can say de-Broglie wavelength for particle P, let us call this as lambda P. So we can write our lambda P is equal to h upon momentum of P, which can be written as, in terms of lambda, we can write this as 1 upon 1 minus 1 upon lambda x minus 1 upon lambda y, which we can take as LCM. So this comes as our lambda x, lambda y, and this will be our lambda y minus lambda x and its magnitude. Therefore, the option B will be correct. Correct. 1 second. Yeah. Next question. It states that two particles move at right angle to each other. Their de-Broglie wavelength are lambda 1 and lambda 2 respectively. The particles suffer perfectly inelastic collision. The de-Broglie wavelength lambda of the final particle is given by. So here we have two particles and they are moving right angle with each other. So I can say that de-Broglie momentum of each particle and particle are lambda 1 and lambda 2. So let us write the momentum as our P1 is equal to h upon lambda 1, and we have P2 is equal to h upon lambda 2, and the particles are moving at right angle triangle. So the net momentum, we are given that particles are moving at right angle. Therefore we can say net momentum let us call this as P will be equal to P1 square plus P2 square, which comes as h upon lambda 1 whole square plus h upon lambda 2 whole square. And we can take h as common, so we get this as p is equal to h and square root of 1 upon lambda square plus 1 upon lambda 2 square. And our wavelength is given as, this can be written as our h upon p will be equal to 1 upon 1 plus lambda 1 square plus lambda 2 square and its square root. And this h upon p is our lambda is equal to 1 upon, this we have 1 upon lambda 1 square plus 1 upon lambda 2 square square root. So we can just cross multiply it. We get this as 1 upon lambda 1 square plus 1 upon lambda 2 square is equal to 1 upon lambda. And now squaring it. So we get 1 upon lambda square is equal to lambda 1 square plus 1 upon lambda 2 square. So the option number A is correct. Correct. Next question. It states that a particle A of mass m and charge q is accelerated by a potential difference of 50 volt. Another particle B of mass 4m and charge q is accelerated by a potential difference of 2500 volt. The ratio of de-Broglie wavelength lambda A to lambda B is. So we are going to find out, we have particle A and B of different mass and different potential difference. So we can say that the kinetic energy of particle, let us suppose that is given as K, will be equal to over Q multiplied by the potential difference. And we can also write that wavelength lambda is equal to h upon momentum p, or we can write this as h upon 2mk and its square root. And k is in terms of q and v, so we can write this as h upon 2m q v and its square root. So we have two particles, therefore we can divide this formula as our lambda A is equal to h upon 2 ma q va square root. Similarly, lambda B is equal to h upon 2 mb, charge is same, and our potential difference, that is our Vb. And we are given lambda A upon lambda B ratio. So we can say our lambda A upon lambda B will be equal to, this comes as our lambda A is our h upon square root of 2m q va, and this is h upon 2 mb q vb square root. Here we can just cancel h and h, and we can write this will be equal to over square root 2m b q vb 2ma q va, and this 2 and 2 Q and Q cancel out, and MB is given to us as 4m. So we can write this as 4m multiplied by 2500. MA is given as m multiplied by 50. And here also this m and m cancel out, and 0 and 0 goes, and this goes by 50. So we get this will be equal to our 2 square root of 50. And okay, and this can be written as 14.114. So we get lambda A upon lambda B is 14.14. Option D is correct. Correct. Next question. It states that if the de-Broglie wavelength of an electron is equal to 10 raised to power minus 3 times the wavelength of photon of frequency 6 into 10 to the power 14 hertz, then the speed of the electron is equal to. So here we are given the frequency of photon. You can say frequency of photon, that is our f is equal to 6 into 10 to the power 14 hertz. And we are given that the wavelength of electron is equal to 10 raised to the power 3 times wavelength of photon. Therefore, we can write that our wavelength of electron is equal to 10 raised to the power minus 3 times wavelength of photon. Or we can write our lambda E is equal to 10 raised to the power minus 3 times lambda of photon. And we need to find out speed of electron. Okay. So first of all, we are going to find out the photon wavelength. So you can say photon wavelength which is our lambda photon will be equal to C upon frequency. C is our 3 into 10 to the power 8, frequency is our 6 into 10 to the power 14. So this gives us that our lambda photon is equal to 5 into 10 to the power minus 7 meters. So based on this, we can find out our de-Broglie wavelength. Wavelength of electron. Okay. So we can say that our lambda E is equal to 10 to the power minus 3 multiplied by 5 into 10 to the power minus 7. This gives us 5 into 10 to the power minus 10 meters. Excuse me, please. Now we can use our de-Broglie relationship. De-Broglie relation, which gives us that our lambda E is equal to h upon mass into velocity. So from here we can say that our velocity is equal to h upon mass and its wavelength. We already calculated all the values, so we substitute, we get velocity is equal to 6.6 into 10 to the power minus 34. Mass we know is our 9.1 into 10 to the power minus 31, and lambda is our 5 into 10 to the power minus 10, and this comes approximately equal to 1.475 into 10 to the power 6 meter per second. So this is option A is correct. A is correct. So these were part 2 of year 2019 mains question, in which we dealt with 10 questions. So this completes all the 10 questions for the part 2 of year 2019. Thank you.